What's up, team? Quick question before we start. Do you actually know end-to-end pipeline architectures? Putting it all together? By the end of this video, you will. Let's dive in. By the end of this video, you'll be able to look at any data pipeline requirement and know exactly which Amazon Web Services to wire together and why. Picture 3 requests landing on your desk in the same week. Migrate an Oracle database to Redshift with near zero downtime. Ingest IoT telemetry and react in under a second. Lock down personally identifiable information columns so the analytics team can't see them. 3 very different problems, 3 very different architectures, and by the end of this video, you'll know how to build all 3. Here's the thing that changes how you design data systems. Almost every real-world pipeline you'll ever build is a variation of one of 5 reference architectures. The requirements look endless, different latencies, different sources, different governance rules, but the shapes underneath repeat. Once you can recognize the shape, you stop reinventing the wiring for every new project. You match the requirement to a template, and then you tune from there. That's the skill we're building today. Here are all 5 on one slide. Batch analytics is the serverless workhorse, S3, Glue, Athena. Real-time streaming is Kinesis Data Streams into managed Flink, feeding DynamoDB with an S3 archive on the side. Near real-time is Firehose dropping Parquet into S3, with Athena querying the moment data lands. Database migration is the schema conversion tool followed by DMS, staging through S3, and Glue merging into Redshift. And the governed data lake puts lake formation over a 3-zone S3 layout, so Athena, Spectrum, EMR, and Glue all enforce the same permissions. Keep these in your peripheral vision. We'll spend the rest of the video unpacking each one. Before we dive in, here's a way to remember which pipeline is which. Think of restaurants. Batch analytics is a buffet prepared overnight, served the next day, cheap per plate. That's your scheduled S3 and Glue pipeline. Near real-time is fast casual, you order online, food is ready in minutes, the menu is predictable. Think Firehose landing data every 60 seconds. Real-time streaming is a sushi conveyor belt, each piece flows past in seconds, custom prepared on the spot. That's Kinesis Data Streams with Flink. Migration is moving the entire kitchen to a new building. The schema conversion tool redesigns the layout, DMS moves the food, and Glue rearranges the menu. Big project, one-time effort, lots of coordination. And finally, the governed lake is the health inspector, same kitchen, same food, strict rules on who can touch what. Different speeds, different costs, different tools, all in this video. Notice that S3 appears in every single architecture. That's not a coincidence. S3 is the loading dock of the warehouse. Trucks like DMS and Firehose drop pallets there. Forklifts like Glue and EMR move them around. And customers like Athena, Redshift, and QuickSight pick up the finished orders. The dock doesn't care who delivers or who picks up, and that decoupling is the whole point. When you see an answer choice that skips S3, that's almost always wrong. Even DMS writing to Redshift quietly stages through S3 under the hood. First up, batch analytics. This is the pipeline you reach for when the requirement is hourly or daily reporting with the least operational overhead. There's no streaming requirement, no sub-second latency, just clean data turned into queryable tables on a schedule. It's the most common architecture in the wild, and it's the one you should default to unless something in the question pushes you towards streaming or warehousing. Let's walk it. Raw files land in S3, typically CSV or JSON dropped there by upstream systems. A Glue crawler reads the new files and writes the schema into the Glue data catalog. From the catalog, a Glue ETL job reads the raw data, converts it to partition Parquet, and writes it back to a curated S3 location. From there, Athena queries it for ad hoc analytics, or Redshift loads it for dashboards and complex joins. Every box on this diagram is serverless. There's nothing to patch, nothing to scale, nothing to babysit. Here's the concrete reason Glue ETL earns its place in this pipeline. Scanning a 1 terabyte CSV file in Athena costs you roughly $5 per query. Convert that same data to partitioned Parquet first, and the exact same query costs about 8 cents. That's a 60 times cost reduction from one Glue ETL job. And here's the underlying mechanic. Athena charges by data scanned, so columnar Parquet lets the engine skip entire columns it doesn't need, and partitioning lets it skip entire folders. That's why nobody in production runs Athena directly against raw CSV. Now the trap answers. EMR for this workload is wrong because it adds cluster management overhead for something Glue ETL does serverlessly. Custom Spark on EC2 is wrong because you're reinventing Glue from scratch. Lambda for the transform is wrong because of the 15-minute execution limit and the lack of native Spark. And manually written table definitions lose to crawlers because schemas drift and nobody updates the DDL the pattern. When you see EMR in the answer for simple CSV to Parquet conversion, eliminate it. Architecture 2 is real-time streaming. The trigger words are sub-second latency, stateful processing, windowed aggregations, or stream joins. If any of those appear in the requirements, the answer involves Kinesis Data Streams and managed service for Apache Flink. This is the heaviest pipeline of the 5, so the question has to justify the weight. Producers, applications, or Internet of Things devices push records into Kinesis Data Streams. Kinesis acts as the buffer with replay and fanout, holding records for up to 7 days. Managed Flink reads the stream and runs the stateful work, tumbling and sliding windows, stream-to-stream joins, exactly once aggregations. The enriched output forks 2 ways. Enriched results land immediately in DynamoDB for single-digit millisecond lookups by downstream applications. And a parallel branch sends raw events through Firehose into S3, giving you a durable archive you can replay months later. End-to-end latency typically falls well under 1 second for this architecture. Here's the moment a Lambda-based approach breaks. Picture a 5-minute session window, group every click from the same user that arrives within 5 minutes of the previous one. Lambda is stateless by design, so Invocation 2 has no memory of Invocation 1's events. The first batch of clicks arrives, the next batch arrives 3 minutes later in a fresh invocation, and there's no shared state to tie them together. The session is already broken. Flink solves this by checkpointing stream state to S3 every few seconds. On failure, Flink resumes from the last checkpoint with exactly once guarantees, replaying events from Kinesis to rebuild any open windows. That's what stateful exactly once processing actually means. And the wrong answers? Firehose for ingest looks tempting because it's simpler, but it has no replay and no multi-consumer fanout. Once a record is delivered, it's gone from Firehose. Lambda for windowed processing is wrong because Lambda is stateless and can't give you exactly once semantics across a 60-second window. RDS is wrong here because it cannot match DynamoDB's single-digit millisecond guarantee for high-throughput key-value lookups at streaming scale. And Redshift microcopy operations from streaming data kill throughput, which is why we land in S3 first and batch load later. Quick recap before we move on. Batch is serverless Glue and Athena on a schedule, the cheapest path for hourly or daily reporting. Real-time is Kinesis Data Streams plus Flink for sub-second latency, stateful windows, and multi-consumer fanout. Next up is the pipeline that sits between them near real-time, where Firehose replaces both the buffer and the processor with one fully managed service. Architecture 3 is near real-time analytics, and this is where a lot of people overshoot. When the question asks for minute-level latency, no custom processing, and no infrastructure to manage, Firehose plus Athena is the right answer. Reaching for Kinesis Data Streams and Flink here is overkill, and the correct answer is the simpler stack. Here's the flow. Producers send records straight to Firehose. Firehose buffers them anywhere from 60 seconds to 15 minutes, and during that buffer window, it converts the inbound JSON into Parquet by referencing a Glue schema. The Parquet files land in S3 with year, month, day, and hour partitions, and Athena queries them, typically with partition projection so you don't even need a crawler. The whole pipeline has no shards to manage, no consumers to write, no clusters to size. Here's why each piece was chosen. Firehose is there because it has 0 shards, 0 consumers, and automatic JSON to Parquet conversion built in. The Glue schema reference is required. Firehose needs it to know how to write Parquet, and this is the part teams forget in production. The S3 layout with year, month, day, and hour prefixes lets Athena skip entire date folders, which reduces data scanned and lowers cost per query. And Athena with partition projection means you don't need a crawler at all. The moment data lands, it's queryable. Amazon Web Services' own documentation makes the case directly. Amazon Data Firehose, formerly called Kinesis Data Firehose, can transform data to Apache Parquet and Apache Orc formats and deliver to an encrypted S3 bucket, enabling much faster and cheaper queries from Athena and Redshift Spectrum. That single sentence captures why this architecture wins. The conversion happens inside the managed service, no ETL job required. The wrong answers here are the most instructive of the whole video. Kinesis Data Streams plus Flink for minute-level analytics is overkill, more cost, more operations, no benefit. A Lambda consumer that writes Parquet to S3 is just reinventing Firehose with worse reliability. Running a Glue crawler over Firehose-delivered data adds cost and latency, when partition projection would do the same job for free. And piping Firehose straight into Redshift creates microbatch copy operations, which kill throughput. This chart compares 3 pipelines on the same scale. Kinesis Data Streams plus Flink at about 1 second, Firehose at 60 seconds, and batch Glue daily at 1 hour. Kinesis Data Streams plus Flink lands you at roughly 1 second end-to-end. Firehose has a hard floor at 60 seconds when S3 is the destination, because that's the minimum buffer interval for the S3 delivery path. And batch Glue daily runs at an hour or more, scheduled. When you read a scenario, find the latency requirement first and you've already eliminated 2 out of 3 pipelines. Architecture 4 is database migration. The shape almost never changes. When the source and target databases are different engines, Oracle to Aurora PostgreSQL, for example, the answer always starts with the schema conversion tool for the schema, then DMS for the data, with S3 in the middle as the staging layer, Glue merging the change feed, and Redshift as the analytical target. Let's walk it. The schema conversion tool runs first as a one-time exercise. It reads the Oracle or MySQL schema, including stored procedures and triggers, and rewrites them for the target engine. Then DMS connects to the source database, runs a full load to capture the initial snapshot, and switches to change data capture mode to tail the transaction log. DMS writes Parquet files into S3 with the change flag in the first column. Glue ETL reads those files and merges the changes by inspecting the I, U, or D flag. And finally, the curated tables are loaded into Redshift with a parallel copy from S3. Here's the way to remember the 2 DMS phases. Full load is the moving van on day 1. It takes everything you currently own to the new house in one big trip. Change data capture is the daily mail forwarding service that keeps delivering anything new to the old address over to the new one. And it labels each item inserted, updated, or deleted, so the new household knows what to do with it. Together, the two phases give you minimal downtime migration. The official DMS documentation spells out the change flag column directly. When DMS replicates ongoing changes through a change data capture task, the first column of every output file marks how the row was changed: I for insert, U for update, D for delete. That single column is what your Glue merge job reads to decide whether to append a new row, modify an existing one, or remove it from the curated target. And here's the part that surprises people. Even when you configure DMS with Redshift as the direct target, it still writes the data to an S3 bucket first and then issues a Redshift copy command to load from S3. The S3 staging layer isn't optional, it's how DMS actually works internally. So when an answer choice promises to skip S3 and load straight into Redshift, that answer is misrepresenting the architecture. This pipeline ends at Redshift, reached through 5 services. Let's walk them in order. The schema conversion tool converts schemas and stored procedures between dissimilar engines. DMS alone will not do this work. DMS moves the data, handling both the initial snapshot and the ongoing change stream. S3 is the durable staging layer, and it's exactly how DMS reaches Redshift internally anyway. Redshift is the analytical target at the end of the chain, loaded with a parallel copy from S3 across all compute nodes. That's how it achieves high ingest throughput, by reading multiple S3 files simultaneously. Glue ETL sits in between, merging the change files by the change flag column to keep curated tables in sync with the source. Now the trap answers. Using DMS alone for an Oracle to PostgreSQL migration is wrong because DMS does not convert stored procedures or complex schema between dissimilar engines. Direct DMS to Redshift skipping S3 in the architecture diagram is misleading. As we just saw, S3 is always there. Writing custom binary log replication scripts is reinventing DMS change data capture from scratch. And the most common production bug, ignoring the change flag column, produces duplicate rows in the curated tables because updates get appended instead of merged. The 4 pipelines we've covered so far all share a common goal: they move or transform data. The 5th pipeline solves a fundamentally different problem. It's not about getting data from point A to point B faster. It's about controlling who can see which columns, which rows, and even which individual cells once the data is sitting in S3. Same storage layer, completely different design challenge. Architecture 5 is the governed data lake. The trigger phrases are column level, row level, cell level, or cross-account access. When any of those appear in the requirements, the answer is lake formation on top of the Glue data catalog. IAM alone cannot do fine-grained access at the column or row level, and bucket policies certainly can't. Let's start with the storage. S3 raw holds the immutable landing data. S3 curated holds validated parquet. S3 analytics holds business-ready aggregates. Each zone gets its own bucket or prefix with its own IAM scope. Above them sits lake formation, integrated with the Glue data catalog. That layer is where column, row, and cell permissions live, where LF tags get applied, and where cross-account shares are managed. Now look at the consumers. 4 engines query through that governance layer. Athena handles serverless SQL Spectrum, Bridges, Warehouse, and Lake. EMR runs custom Spark and Hive. Glue ETL handles the transformation jobs. One lake formation grant covers all 4. Amazon Web Services designed this integration as a single control plane. Lake formation uses the Glue data catalog to enforce access control across the major analytics services: Redshift via Spectrum, Athena, Glue ETL, and EMR. That's the unification you can't get with IAM alone. One grant statement, enforced consistently across every query engine you use. Here's why lake formation tag-based access control scales where manual grants don't. Picture 40 analysts across 3 teams, all querying the same governed tables, and 3 of those columns contain personally identifiable information. Without tags, that's 40 analysts times 3 columns, 120 individual grants to manage, repeated every time someone joins or leaves. With LF tags, you tag those 3 columns once as sensitivity equals personally identifiable information. Then you grant or revoke by tag, not by column. Onboarding a new analyst becomes a single statement. Revoking access when someone changes teams becomes a single statement. That's how governance actually scales past a handful of users. And the wrong answers. IAM alone is wrong because IAM policies operate on objects and prefixes. They can't grant access to specific columns or rows within a table. Bucket policies for fine-grained access are the wrong tool entirely. Data brew is a common distractor here. It prepares data, it does not govern it. And per table grants for 100 principals across 100 tables means 10,000 individual grants to manage, which is why LF tags exist. Let's zoom out and look at service selection across all 5 pipelines. The default is to pick the serverless option, Glue over EMR for standard ETL, Athena over Redshift for ad hoc queries. Firehose over Kinesis Data Streams when the requirement is just delivery. Step functions over custom Lambda chains for orchestration. The heavier service only wins when there's a specific justification, EMR when you need Hive, HBase, or custom Spark. Redshift when you have dashboards, complex joins, or sustained load. Kinesis Data Streams when you need replay or multiple consumers. Custom code only when there's a clear functional gap. Here's the decision rule stated as plainly as possible. When 2 services solve the same problem, pick the more managed one unless the scenario gives a specific reason not to. Phrases like least operational overhead, no infrastructure to manage, or minimize ongoing maintenance are all pointing you toward the serverless choice. The scenario has to argue for the heavier service explicitly. Silence means serverless wins. Athena and Redshift overlap enough that scenario questions blur them on purpose. Here's the actual decision line. If the workload is ad hoc, bursty, and fewer than about 20 concurrent users, Athena wins. You pay only for the bytes you scan, and there's no cluster to keep warm. If the workload is sustained business intelligence dashboards with 50 or more concurrent users hitting the same tables all day, Redshift wins. Provisioned capacity gives you predictable query times and predictable cost. The inflection point is concurrency and consistency, not data size. Here are the 5 anti-patterns that appear most often as distractors. Flink for minute-level analytics. The correct shape is Firehose and Athena. EMR for simple CSV to Parquet conversion. Glue ETL does that serverlessly. DMS without the schema conversion tool for a heterogeneous migration. You need both. IAM alone for column-level access that requires lake formation. And streaming straight into Redshift in micro batches, Firehose to S3, then a batched copy. Memorize the wrong combinations and you can eliminate them on site. Here's the keyword decoder for the whole video. Subsecond or stateful windowing means Kinesis Data Streams plus managed Flink. Within a minute or no infrastructure means Firehose into S3 into Athena. Hourly or daily with least overhead means batch Glue ETL plus Athena or Redshift. Oracle to Aurora, or minimum downtime, means the schema conversion tool plus DMS full load and change data capture. Column, row, cell, or cross-account access means lake formation on the Glue data catalog. And shared metadata across engines means the Glue data catalog itself. The tiebreaker: when two options both seem to work, pick the more serverless one. Remember those three problems from the start of the video? Oracle to Redshift migration, that's schema conversion tool for the schema, DMS for the data, and Glue to merge the change flags. IoT telemetry under a second, that's Kinesis Data Streams plus managed Flink, because you need stateful windows and exactly once. Personally identifiable information column lockdown, that's lake formation tag-based access control. S3 sits in the middle of every pipeline, even DMS to Redshift stages through it. Subsecond means KDS plus Flink, within a minute means Firehose, hourly means batch Glue. And on Firehose, it needs a Glue schema reference to write Parquet, that's the detail teams forget in production. When two services would both work, pick the more managed one unless the scenario tells you otherwise. One video, 5 templates, every combination covered. That wraps up end-to-end pipeline architectures, putting it all together. The Amazon Web Services Certified Data Engineer Associate has more videos coming on the trickier topics. Subscribe so the algorithm tells you when. Thanks for watching.